In the last video we got as far as finding the entry point for the firmware code that's in the ROMs. From that point on it gets significantly more difficult to proceed with the disassembly and reverse engineering of the system. That's primarily because, as in this case, when you don't have a schematic diagram or any technical information, we have no way of knowing how the overall system's wired up other than what we can see. We don't know how the firmware addresses the individual devices, we don't know the memory map, we don't know how the various timing functions work. And anyone familiar with a device like this will know that because we're driving a mechanical system with many mechanical parts, stepper motors, print heads, keyboards, that sort of thing, then the firmware can't simply go to a single task. For example, a stepper motor, it can't step the motor on, wait for that function to finish and then move on, because that would take up too much time and the processor would be sitting there waiting for thousands of cycles while the stepper moved. So the way systems like this are generally put together is there will be a series of constructs such as state machines, and the idea there is that each of those state machines will effectively maintain the state of an individual function or task, such as driving the paper. That can be an individual state machine, and each state is allowed to proceed without the attendance of the microcontroller or microprocessor, and the microprocessor will move on to the next state machine, update that, and it will keep going around processing all the currently active state machines, making sure that as each state is reached, so if it's trying to step a stepper motor for example and it's running a timer to allow that step to finish, then when that step has timed out and finished, it will then move that state machine on to the next phase, and it will do that for all the state machines that are currently active for whatever the process is it's currently trying to complete. That means that in order to be able to really do much with a machine like this when we're trying to reverse engineer it, we need to find out what each of the individual control elements is doing and how it's addressed by the firmware. What makes it even more difficult with an old machine like this is, firstly, there is a lot of analog circuitry in this, and some of that analog circuitry fulfills what would otherwise be digital functions. So in other words, there's a huge board at the back of this machine, and amongst having power supplies and stepper drivers, it also has various clock signal generators and timing functions, and they are mostly used for things such as timing steps, even though there are timing loops within the firmware, and also generating tone signals for the beeper, that sort of thing. It's really a case of looking into the firmware in a logical manner and trying to figure out how each of these different elements is addressed, and then we can start looking through the firmware to see how the firmware overall controls the machine. Firstly, we need to look at what is actually in the machine in terms of the hardware that will be addressed. We know we have a 6800 processor, and then what we have that is used for most of the hardware interfacing is a series of 4 PIAs. Anyone not familiar with this type of device, it's well worth having a look at the data sheet. So these particular devices are the MC6821. These are quite interesting devices, and they essentially are 2 8-bit ports, bidirectional ports, and it also has the ability to respond to external interrupts. So it has a couple of interrupt pins. What makes this a fairly unusual device is that one of the ports allows its pins to be used as inputs and outputs at the same time, and that does make decoding this operation quite a lot more difficult until you figure out exactly what each pin is doing. So that's really the first task, is to try and figure out how these are configured when the machine boots up. Now, if you're familiar with embedded systems, you'll know that one of the first thing any embedded system has to do is to initialize and configure any devices such as PIAs, because it can't use them till it's done that. And most designers will do that right at the beginning of the code, not necessarily in the first lines, but in the first process that is run after a reset is to configure any devices that need any form of configuration. So that's usually a good place to start. One other thing that makes working on old machines like this quite complex is if you're familiar with programming things like Arduinos and PICs, then really you're spoilt for memory, for program space. You get a PIC with a megabyte of program memory. That's full program width. Each address will hold an entire instruction along with its parameters. That's not the case with something like this. This has 3K of ROM, and in that 3K it has to have everything for performing every function, timer, that it can't hand off onto an analog circuit. Because of that, there is a huge amount of optimization in the way that the 6800 processor accesses the hardware, and that's going to become fairly apparent in this video when I go over the initial part of the firmware program. So as I said in the previous video, we got as far as finding the entry point for the firmware. So that was at address 3A1C. So this is where we'll end up immediately after a reset or a boot up. And the first thing that the machine does is to disable any interrupts. That's something that, again, you do quite often in embedded systems. You don't want an interrupt occurring because you haven't initialized the machine yet, and if the interrupt is trying to use any device that needs initializing and the interrupt occurs before that initialization is complete, then the system will probably crash. So it starts off by disabling the interrupts. It then clears the index register. Now I mentioned that there needs to be quite a lot of optimization on old machines like this because of the limited ROM space, and this is a very good example of that. If we look at the next page, then in the previous listing I showed you, I had removed this block of code just because it's always the same, and once I'd gone through it and realized what it did, I didn't need to go back over it. I made a note of it, all the values that were addressed. Now again, this is the result of the work that I've done on this, so all the comments and the labels are what I added as I was going through it. But in terms of optimization, what this block is doing, although it's quite a small block, it's initializing every device in the machine. And the way it's doing this is quite clever. It's a technique that is often used on older machines like this. If you're familiar with the instruction set of the 6800, you know that you can use various addressing modes for the memory. So in essence you can use a pointer if you want to, and then you can increment the pointer to point to the next memory address, and it's a very efficient way of running through several addresses in sequence, and it's efficient both in terms of speed and program size. This goes one step further because you can also use instructions such as push and pull, which are normally used to put values on the stack or take them off the stack. But you can use the same mechanism to address any part of the program space that you want. Now the way this works is it uses the pointer register to access data and or RAM areas or device addresses, and it uses the stack pointer for the same purpose. So effectively it uses the stack pointer in direct addressing mode pointer, and it uses those two to look up values on a table. So although the reverse compiler saw this as code, I eventually figured out by going through this, which I'll show you in a minute, that it was actually using these values as a lookup table for values to load into the PIAs. So it starts off by loading the required values into the RAM addresses, and you can see that by virtue of the address range that it is accessing. And I'll show you the memory map in a minute that I worked out by looking at this. Once it's loaded the RAM with the required values, it then moves on to use the two pointers to retrieve values from the table and put those into the PIAs. If we look at the memory map for the devices, then we have the PIA addresses. Each PIA, these are the 6821 devices, occupies 4 address spaces. There are 4 registers within it. There are 2 for configuration, 1 for each of the 2 ports, and 2 status, again 1 for each of the 2 ports. And they are mapped to 8004 up to 8020. So in other words, there's a bit that's used to access each of those registers. And if you look at the data sheet for the device, you see it has a number of chip select pins, and they're just wired up in such a way that they respond when the correct address is accessed and when bit 16 is set. Moving on to the RAM is mapped between address 0 and 1FF, and the stack is located at address 01FF, and as values are pushed onto it, then that will decrement and the values are placed at lower addresses as more values are put onto the stack. And then as the values are popped off, then you go back up towards 1FF. And then below that, below the stack down to 0, are all the variables. So anytime we now see a value below probably about 100 hex, we know it's a variable. There's also a circular buffer that's used in this, which I'll show you in a different video, that's used to handle and buffer data coming in through the serial port, and that is located in this same area between the variables and the bottom of the stack. There are 4 memory chips in the device, and they are mapped to these locations. They're 6810s, so they're 128 bits by 8. So each one occupies 80 hex bytes or memory locations, so they're mapped to these addresses. So that was quite easy to figure out just by attaching the logic analyzer to them and seeing what address was present on the address bus when they were accessed. And then we have the async chip, so that's this device down here. That's a 6850, and it's mapped to address 8040, and again this is the binary address that is used to access it. There are 2 addresses within that device. Again, there's a configuration and a status or data register. There are other devices mapped into the address space, but we'll look at those another time. These were the basic ones I discovered initially by looking through the initialization code. So I won't go through this entire block, but what I'll do is I'll trigger at the beginning of it as we did in the previous video, and then we'll just step through the first instructions to show you how I use the logic analyzer to figure out what was going on within this block of code. So I'll relocate the camera to point at the analyzer, I'll reconnect the analyzer to the ZIP30, and then we'll capture the start of the program entry point. So looking back at the analyzer screen, I've got it configured to capture the entry address as we did in the previous video, So I'll boot up the zip30 and we should capture the program entry point. So there we are, we've captured FFFE, which is the program entry point. So I will start scrolling through so we can see the start of the code itself. And there we are. We have 3A1C, which is indeed the program entry point. Now, what's apparent here is that the program is held in reset for quite a long time when it first boots up. So there is a delayed reset on this machine. So you just need to keep scrolling across until you get to the end of that delay. But in the meantime, it's held at the reset vector. And then once the 6800 starts to run, once the reset's been released, then, because as we looked at yesterday, the reset vector at FFFE will redirect the code to the program entry point at 3A1C, which is what it has now done. So if we look at that in the listing, we are now here. So we've jumped to 3A1C, and the first instruction is a disable interrupt. So that is a 0F instruction, and indeed that's what we have on the screen. So the next instruction is at 3A1D, and that should be load DX with 0, DX being an index register. This is the indirect addressing register that I was talking about. So we should see, starting at 3A1D, value CE0000. So 3A1D, we have CE followed by 0000. So that is at 3A1D, 3A1E, and 3A1F. So that then loads LDX with a value of 0. You just then carry on in the same way through the instructions, and as you go through you can start to read the actual data values and the addresses, and it's the addresses that we are interested in here because we're trying to figure out what it's trying to address and where those particular components are. So if we go on to the next page, to save some time, we know that the first block is loading the RAM, and this does loop around a bit. So what you can do is come straight back down to here, and this will load the PIA values. So what we'll do now is we'll restart the machine, but this time we'll trap it at 3A4B. In fact, I'll trap it at 3A4C so that we don't get caught up by this loop. So I'll enter 3A4C as the trigger. And we'll go back to the waveform. I'll turn the zip30 off because we want to capture it at startup. So the analyzer waiting for its trigger. Start up the zip30, but if you remember we've got a delay now, so I'll set that back to 0 to take us back to the trigger point. And now we can see 3A4C is what we've captured, and we are now at this point in the code. So we're down here. 3A4B is what we're looking for, and you can see that is the previous address, but we went one further to make sure we captured the right address. You can now start going through and seeing what values it picks up. So I didn't know this was a lookup table when I first started. This was just interpreted by the decompiler as code. So I started stepping through this code by following through the individual instructions, and then I could see that what it was doing was using the two pointers, the index pointer and the stack pointer, to pull values from this table and then put them into certain addresses, and when you look at those addresses you'll see that they are in fact the addresses of the PIAs, and I confirmed that by hooking up the analyzer to the PIAs and capturing this particular point or this sequence for each PIA in turn, and making sure that the values I saw being put into it matched what were in the table. And then I was able to sort of reconfigure this, lay this out in the way that it's actually used, and then comment all this code to show that it was in fact loading the PIAs with their initialization values. And you can see this up here. It's put the value of the last PIA. Now the reason it's put the value of the last PIA, and I'll just confirm that. If you remember the address of the last PIA, I determined it to be 8020, and once I'd got to this point in the code, bear in mind I didn't know at the time what was at this address, I found that the analyzer was accessing PIA 11 with this value. The reason it starts at the last one is because it's using the stack pointer to get these values from the table, and because the stack pointer is decremented after each read, then it makes more sense to start at the top and work down, and that way the system is more efficient. You don't need to keep reloading the pointers. So LDX is incremented after each use, and the stack pointer is decremented after each use, and that's automatic. It's done by the processor, so it saves you having to do that in the code itself, and it saves a lot of code space, and it saves a lot of time. So all the code does is it runs through using the two pointers to load the values into the PIAs. What I did from that point is to look at the values that were being put into the PIAs. So if you look at the values in the actual table, you can then figure out, based on the spec sheet of the PIA, how each one is being configured and what each of the pins on each of those PIAs will do, whether it's an input, an output, whether the interrupts are enabled, etc. As I say, it's time consuming, so I won't go through all of it, but you can see that because we've now captured this, in fact I can turn the zip30 off, and we've captured this, so we're not controlling the zip30 through the analyzer of course, but we do now have the full sequence going through the initialization. And what you can do is just follow this through, seeing what's going on. So again, you can see here 8022 is the second register in the PIA 11, the last PIA, and as you go through this it becomes very obvious very quickly what each particular part of the system is doing. Once you know how the PIAs are configured, the next step is to figure out what they're controlling or what they're reading, and so we'll look at that in the next video.